Today, we'll be talking about images formed by lenses. A converging lens is thickest at the middle and thin at the outside edges. When the object is outside the lens's focal point, the image is real, inverted, and on the back side of the lens. When the object is within the focal point, the image is virtual, upright, enlarged, and on the front side of the lens. Diverging lenses are thick at the edges and thin at the center. If the object is anywhere in front of a diverging lens, the image will be virtual, upright, reduced, and on the front side of the lens. Just like with mirrors, we have some sign conventions that we can follow to use these equations for both kinds of lenses. It is important to note that the object and image location are not the same in terms of signs. The object location is in front when P is positive, and the image location is in back when Q is positive. In our first example, we have a converging lens used to read the fine print in a contract. The lens is held 9 centimeters from the print and produces a magnification of positive 2.5. What is the focal length of the lens? Taking the fine print to be an object, we can use the magnification equation to solve for the distance of the image. Plugging in a magnification of 2.5 and an object distance of 9 centimeters, we find that the image distance, Q, is negative 22 centimeters. Using the lens equation, we plug in 9 centimeters and negative 22 centimeters to find that 1 over F is 6.6 centimeters. But again, this is just 1 over F. We need to take the reciprocal to find that F is 15 centimeters. In our second example, we have two converging lenses with focal lengths 15 centimeters and 25 centimeters that are placed 18 centimeters apart. An object is 8 centimeters to the left of the 15 centimeter focal length lens. Where is the final image formed? We can start with the lens equation to find the image produced by the first lens. Plugging in the focal length of the lens, 15 centimeters, and the distance of the object, 8 centimeters, we find that 1 over Q is negative 5.8 centimeters. Taking the reciprocal, Q is negative 17 centimeters. So the image of the first lens, shown in yellow, will become the object for the second lens. The image is 17 centimeters away from the first lens, and the first lens is 18 centimeters away from the second lens. So the total distance between the image and the second lens is 35 centimeters. Using this, we can plug 35 centimeters in as the object distance and 25 centimeters as the focal length to solve for 1 over Q2, and then take the reciprocal to solve for Q2 being 87.5 centimeters. So the final image produced by the second lens is 87.5 centimeters to the right of the second lens.